Here we have an example of a titration problem involving a weak acid. Here we have acetic acid. When we have weak acids or bases in titrations, we need to use our ICE table. In this example, we have a titration of 20 milliliters of 0.3 mole per liter of acetic acid, a weak acid, titrated with a standardized sodium hydroxide. What is the pH at the following points? Before the titration begins, after 10 milliliters of the base has been added, at the equivalence point, and we're also going to select an appropriate indicator to use. So this is our reaction here. Before adding the titrant, the pH will be a result of the weak acid in equilibrium with water. Here, this tells me that I'm being titrated with the sodium hydroxide. So in my Erlenmeyer flask, I have my acetic acid, and in my burette, I have my NaOH, and I'm going to complete my titration here. So before, we want to figure out what is going on in this Erlenmeyer flask. So we have acetic acid, and it's reacting with water. Remember that it's an acid, it's going to donate a proton. It will release CH3COO negative and produce a hydronium ion. Initially, we have 0.300 moles per liter, nothing of our acetate ion and nothing of hydronium. We're going to change by a factor of X, so we're going to decrease for our reactant and increase for our products. We can check the approximation method because we know the Ka value of acetic acid is 1.8 times 10 to the negative 5. So 0.300 divided by 1.8 times 10 to the negative 5 is greater than 500. This tells me that my concentration at equilibrium will remain at 0.3, and I will have X and X. Next, I'm going to set up my Ka expression. At equilibrium, I have hydronium and my conjugate base, CH3COO negative, over my acid. I'm going to plug in the values that I know. 1.8 times 10 to the negative 5 is equal to X squared divided by 0.300. When I solve for X, I get 2.3 times 10 to the negative 2. I have 2 sig digs here for my Ka value. When I solve for my pH, I'm going to get negative log 2.3 times 10 to the negative 3. I had 2 sig digs, so that turns into 2 decimal places. My pH is 2.63 of my weak acid. Next, I want to see what will happen after 10 milliliter of my base has been added. So I'm not yet at my equivalence point, but I'm going to add just a little bit of my base to see where my pH is going to change. We have to do a stoichiometric calculation to figure out how much of acetic acid is left. So first I'm going to calculate my moles for both. Starting with my base, I have 0.1 liter times the concentration of my base, giving me 0.0030 moles. For my acid, I have 20 milliliters, or 0.020 liters, times my concentration, giving me 0.0060 moles. To find out how much I have left of my acetic acid, I'm I'm going to take my excess, which is acetic acid, 0.0060 moles, CH3COO. And I'm going to figure out how much I used when I put in this amount of moles of NaOH. I have 0.030 moles of NaOH, and for every 1 mole of NaOH, I have 1 mole of acetic acid, leaving me with a final amount of 0.0030 moles of my acetic acid. Now that I have my moles of acetic acid left over after I put in 10 milliliters of my base, I'm going to calculate my concentration of acetic acid. Taking that amount of moles and dividing by the total volume of what I put in from my base plus what I put in from my acid. This gives me a concentration of 0.100 moles per liter. I'm also going to have to find my concentration of my acetate ion, because when I put in my sodium hydroxide, I'm going to form sodium acetate. So my acetate ion is going to be present in my solution to some extent. So I'm going to figure out, okay, this is based on my 0.300 moles of sodium hydroxide. For every 1 mole of sodium hydroxide, I have 1 mole of my acetate ion, giving me 0.300 moles of my acetate ion. And I need to divide this by my total volume from when I mixed my acid and my base. So again, I have 0.30 liters, giving me a concentration of 0.100 moles per liter for my acetate ion. Now that I have my value for my acid and my acetate ion, I'm going to use my ice table to figure out what my changes and what my new hydrogen ion concentration will be. So I have CH3COOH plus water will give me my acetate ion and hydronium. Initially, I have 0.100. When I put in 10 milliliters of base, I have a new concentration that I solved for here. And I also have my acetate ion formed from making my salt. So this is existing initially. I have nothing of hydronium here yet. There's a change, minus X, plus X, and plus X. I'm going to use my approximation method to see if I can, at equilibrium, say that I have the same amount of both. 0.100 divided by 1.8 times 10 to the negative 5 is greater than 500. So I can use my approximation method here. Now, I want to solve for my value for my hydronium ion. My Ka is equal to 1.8 times 10 to the negative 5. I have 0.10 for my acetate ion times X divided by 0.100 of my acetic acid. I can see that these will cancel out, and my X value will be 1.8 times 10 to the negative 5, same as my Ka. When I put that in to my pH calculation, I have negative log 1.8 times 10 to the negative 5. Remember here I have 2 sig digs, so my final answer needs to have 2 decimal places. My pH will be 4.74. Let's review what we did here. Number 1, we found our moles of our base that we added and our acid. Then we calculated how much of my acid is left over, how many moles. Then I found out what is my new concentration of acetic acid that I'm able to put in here. I also had to calculate my acetate ion because I'm forming acetate when I put in my base. Then I put into my ice table my values so I could solve for my hydrogen ion concentration. I used my approximation method. I solved for X, and then I solved for pH, and I checked my sig digs.